like to just introduce myself very quickly. I'm Vanessa Moffat. I'm on the advisory board for the Data Center Alliance, which is a trade association for data centers in the UK. I also work for EchoSense as a channel partner manager. If I could ask the panelists to also introduce themselves. Alex first.
Yeah, sure. Hi, everyone. Great to be here. My name is Alex Brew, and I'm the Regional Director for Northern Europe for Vertiv.
Thank you very much. And Keith?
Hi, I'm Keith McLean-Martin. I'm the Technical Director here at Pillar Power Systems here based in the UK.
Thank you, Keith. And Tor?
Yes, so hello, I'm Torbjörn Minde from RISE, Research Institute of Sweden.
Thank you. So today we're talking about meeting the challenges of high density compute. And it's an area close to my heart, not least because I work for an AI company, but also because HPC has potentially massive implications for the planet. It's not really a completely new idea, but the scale of the demand that we're seeing now is immense. I've seen figures as high as 38 gigawatts of data centers that might be required to support the predicted demand, which seems a lot. There's no regulation around this. There's nothing stopping or guiding the growth. For example, the picture behind me, that was created by AI in some HPC data center somewhere. I don't know if this is a good use of energy for our planet or not. And the other day, Mark Butcher on LinkedIn, he said that hyperscalers are committing billions and billions of dollars to creating new AI, HPC focused data center capacity. But they also have net zero targets, and with a target date of 2040 or earlier sometimes. So, Keith, how much of a problem are we looking at here? Can we actually deliver on our ambitions? What are you seeing?
It's an interesting challenge to face. I think many people have been facing challenges with gaining the power infrastructures to support even the current demands that we're looking at, let alone this potential 4, 5, even 10-fold increase in power demand that these facilities might be looking compared to the conventional data centers, even these large-scale hyperscale facilities that have already got very large power footprints. We're already facing a creaking grid to support this, and quite how the infrastructure is going to be made available, or the power infrastructure to support it, and manage the generation of heat output from this. Not only the usable sort of computational power, but everything that is wasted as well alongside this. So the challenges are immense, and how we can do this is going to be very interesting, but it's going to, I think, it's going to drive us all to look at how we design the data centers and actually start with a fresh piece of paper again and look at the design again from the base up, and reinvent perhaps the infrastructure and how we deliver these data centers and the look.
Yeah, absolutely. And you were talking about potentially restructuring the grid a little bit, or maybe adding microgrids. What's your feel on how this will develop?
Well, I think in the world that we're living in, we've got to, as data center sort of power providers and solutions, we've got to look at not only delivering the power requirements that we have directly on site, but also perhaps offering support to the local area, whether it's grid services, whether it's heating services to the local communities. We've got to, I think, look at not just taking from the grid, but offering something back as well as something different. So by implementing perhaps a microgrid type power solution in supporting the local data center infrastructure, whether that's multiple campuses, multiple facilities into a major center, sort of an energy center, it's possible to perhaps deploy these services to the local area, but then support the grid to deliver services and avoid perhaps unnecessary deployment of dirty, carbon intense generation, offer services back to sort of mitigate those needs, and work in collaboration with that local area as well.
Sounds like a bit more flexible offering, so maybe adding a bit of flexibility into the system.
It has to be. I think we can't be fixed on a very structured deployment. We have to look at how power is going to be used. It's going to be deployed at different times. And you've got to look at a flexible power infrastructure that can take that power, deploy it when it's needed, where it's needed, and in turn, not only deliver the sort of the critical power requirements for the data centers and the campuses, but also offer some services back to the grid to aid or help that aging and creaking infrastructure that is needing support wherever it's possible. And that's in both the form of power and in heat deployments, perhaps as well. With that energy center, you can more easily capture heat and perhaps look at reuse or deployments elsewhere.
Sounds very sensible. And Alex, you're seeing some different uses of energy, because I guess we've got to look at where we are as well in the world and what we can actually use around us. So tell us a little bit about what you've seen and how potentially we could do things differently in the future.
Yeah, I mean, Keith's point is absolutely critical, right? If we're going to see the sort of growth that is being talked about within the segment, then circular economy-led operating models for data center sites is almost an absolute fundamental. They do harvest or harness significant power reserves. They do have significant byproducts in terms of heat. And so for the companies that are deploying to, fulfill their obligations to meet the demand in terms of IT compute that the world is supposedly needing off the back of this transformation that's taking place, they have to be offering up those reserves for more sustainable practices and how they interface with society, right? So if we're going to see excessive demand on the national grids, then naturally we're going to be wanting to invest in more renewable sources of power generation, and using the power reserves that the data centers have is a key enabler to wider adoption of the likes of wind power or solar and so on and so forth. But I think separate to that, what we may see is also a transition as we start to get a more mature understanding of the likes of hydrogen fuel cells and other variants of on-site power generation. We may actually see that some data centers are investing in their own primary power generation on site and actually starting to use the grid as backup. So they have the capacity to kind of isolate themselves and be a little bit more autonomous, with respect to their own power consumption. Naturally, that changes the CapEx model for a lot of operators who are looking to build out, talking about significant investments. And I think, also geographically speaking, a lot of the AI workloads are, they're not dependent on proximity often to a lot of the sort of larger urban hubs and those core markets that we know about. Naturally, we will see, significant IT loads being deployed across the flat B markets and some of the other emerging hubs. But, the Nordics in particular, which is an area that I look after, we're seeing, huge interest in investment there right now because the connectivity is good enough. And for these AI, engines to be operating, you don't necessarily need, super low latency connectivity with the user, which means that brings the kind of the user case of investing into areas like the Nordics, where they have a very green grid with very high levels of guaranteed power, which is relatively cheap and well assured, particularly with hydro, but also the investment they're doing in other areas. And so it's kind of changing the landscape a little bit in terms of some of the traditional expansions of co-locations and hyperscalers that we've seen over the last few years to now this kind of net new AI development tier that's coming in, which is operating under a slightly different set of not rules but parameters in terms of what's driving the site selections and developments.
That's interesting. And you mentioned potentially having the grid as backup. If you've got, let's say, 20 megawatts as backup from the grid, you still need all of that infrastructure built out. How, in your experience, how are the grids actually taking to that request? Do you think that's an easy request to make?
No, I would say no, and it's not a topic I'm hugely experienced on, so I wouldn't want to talk myself into a hole on that. But naturally, I think isolating yourself from the grid and primarily running on your own power generation is of course good. But like you say, to have a resilient redundancy strategy, you still need to ensure that the grid has that availability, right? And the unpredictability of outages would still potentially create a risk profile that some organizations weren't prepared to use. It depends on the nature of the facility, the disaster recovery strategies they have in place. We do see, particularly in the enterprise space, if we get away from, the hyperscalers, now, a lot of them have increased resilience within their network architecture across different data center sites. So it's just about building out the autonomy, and often larger autonomies using bigger batteries or battery energy storage systems, perhaps, to allow them to migrate through those kind of disaster recovery periods to transition to other sites. And then they don't necessarily need dependency on the grid even to back up. So there's different ways that you can look at it. But it's kind of it's an option that we see on the horizon. It's not something that is that is very well developed in terms of user cases right now.
Yeah, I think it's really interesting because Uptime obviously for years and years have said that generators are the most reliable source of energy. And then, everything else has failures potentially. But I guess it depends on which country you're in, because if you're thinking about the UK, our grid's fairly stable, but in Africa, potentially in some areas, it's not as stable. And I think looking at the design with a like a blank sheet of paper, as you were saying earlier, Keith, that's don't just make assumptions about what this data center should look like. But I'm just thinking as well, because the densities are increasing, Tor, what high density installations have you seen? Are there any safety factors that we need to consider as well within the data center?
Yeah, that's one of the things I've been raising a little bit lately. Coming in with 100 kilowatt to rack and then go out with the heat, maybe with liquid, probably liquid. It's starting to get a little bit of a challenge, the safety of the personnel or safety all over the place in that data center full of 100 kilowatt racks. So that is one area that needs attention now. How do we make it work and safe, and how do we monitor it and detect errors and etc. It will be more important now, I think.
I think, wandering around data centers normally, it's just go around in your normal work gear. You don't have to worry about, anything really happening. But it seems like it's becoming a bit more of a safety conscious environment. So, you've got the increased air density, you've got potential for different kinds of failures you were mentioning the other day, Tor.
Yeah. Yes. Leakage, you have, if you have a lot of oil there, of course, the oil is electronics safe, but still, fire protection will need to be integrated into all this, and have the power cables that I'm just thinking about 100 kilowatt to rack and 100 kilowatt out again of liquid. It's going to be full of cabling and piping, and how are you going to do the maintenance? That's another question. You don't get hold of the servers. It's full of cables or PDUs and stuff. It will be a very interesting design. So I think a white sheet, a new design. And then we need some machine learning algorithms that do have monitoring all the devices for failures. That will be very important.
Yeah, much more tools in place, I think. So this is a question for all of you, actually. What do you think the changes will look like in terms of new data center developments? And I'll start with Alex.
I think it's at the moment, one of the big challenges that we're seeing is how do we kind of hybridize the traditional data center architecture to be able to cater for the higher density liquid cooling based IT platforms, and then also a level of traditional air cooling as well. A lot of the deployments that the customers are looking to make, they're not exclusively one or the other. And if you're talking to a co-location business, some of them will be building exclusively for single clients, but others, they need to design and develop sites that have the ability to cater for customers with different requirements. So that's proving, a kind of a fresh challenge. The traditional kind of rack densities of up to 6, 8, 10 kilowatts under an classic air-cooled strategy, of which there's different iterations that you can work through, all with their own respective merits, but the fundamental principles of how you're cooling are very much the same, right? You're using a body of air and changes in temperature to extract the heat and remove it from the building. And now we're talking about liquid cooling platforms that, particularly when you get onto direct-to-chip, that some of which are using in-rack CDUs, some of these which are using in-row CDUs. There are instances where tenants are looking to bring this infrastructure in themselves, and then you have a whole kind of challenge around your SLA agreements that you have with your customers, and then you've got other customers that are looking for the data center provider, the co-location company, to facilitate the infrastructure themselves and take responsibility for it. But because we're talking about such a close coupling of IT hardware now with the critical infrastructure, before we had this very clear and obvious barrier that was the air, and people know air and they trust air. It's relatively harmless in a data center environment, at least anyway. And actually now what we're looking at is something that's far more intertwined. So we have invested heavily in our relationships now with the likes of NVIDIA and other IT hardware providers and the chip manufacturers, because of the need of the understanding of that space, and to help our clients navigate those steps forward into what these hybrid architectures are going to look like, but also because we know that ultimately they're going to look to us for how they service and support and fulfill the SLA requirements that they're being asked to sign up to. It's a disruptive trend, and the nature of how we can prep ourselves to also go on that journey with them is really, really important. And I think I mentioned when we did the last one of these sessions back in November, that control element and the kind of cooling ecosystem that governs all those different hybrid technologies, the traditional air cooled that will still very much be required, some of which will need to be higher density than just conventional perimeter cooling. Plus then the liquid cooling element running on common chilled water loops, chillers that need to be able to cater for higher temperatures and operate in more extreme environments, particularly when we look towards the Nordics. It's not so much the peak heat, the peak external temperatures in terms of the hottest days of the year that are concerns there, it's the coldest. So there's a lot of different variables that we need to consider, and that's without even going to the power piece, which I'll pass on to Keith to elaborate on a bit.
Go on, Keith.
Yeah, obviously the challenges of deploying the power into these mass sort of variants of densities is a challenge, especially if we're trying to standardize a solution throughout and the infrastructure. Deploying one hall that might be pulling at this 10, 20 kilowatts per cab versus 100 kilowatts per cab means you would normally have to have completely different infrastructure to support it. I think what we're seeing is if we can deploy sort of intelligent, sort of developed solutions that can manage the deployment of variable density power from the same architecture, that's got to be key to sort of simplifying the architecture on the power side that can support these mass variances in power requirements, power demands. So if you can get an architecture that can distribute the power, we see sort of isolated parallel rings being a key infrastructure support that allows the deployment of different densities without differentiating your power infrastructure. So standardize on your power infrastructure chain, but at the deployment end, you can then adjust that according to the densities that you're pulling in different data halls. This maintains the flexibility throughout the architecture, but also standardizes the solution in the day one build-up infrastructure.
It sounds like hybrid cooling and hybrid power to me.
Essentially, and what we're seeing is also we're all talking about the reuse of heat where possible. Obviously, capturing the heat from the IT infrastructure is one part of it, but also all of your power infrastructure. Instead of deploying just cooling systems or air management systems to look after the cooling associated with the UPS and the generation that we're talking about, if you're deploying primary power generation on the site, you've now got opportunities to look at that base loading to deploy combined heat and power into that, and that's deploying both cooling and heating into that circuit. But also the UPSs offer opportunities to recapture some heat from their systems. Options are available for direct air-to-water heat exchangers coupled with the UPS systems, but you can also recapture it on the air ducts and on the return air systems as an option as well. All of this can be deployed as to the sustainability of the power infrastructure and deployed elsewhere to whether just maintain heat into the generator bays to maintain them at the optimal temperature. But if you can then combine those with other systems, perhaps heat pumps and things like that, you can then deploy them into other applications as well in the campus-wide sorts of perhaps solutions.
All very interesting points, and yeah, there's loads. Sounds like more opportunities to use the waste heat. Tor, you had an interesting point on the direct-to-chip cooling and how that affects the waste heat temperature.
Yeah, I listened there. Alex was talking about solid or fuel cells, and I would like to talk about solid oxide fuel cells. We have a project together with Vertiv on this EU-funded projects, but we also did another EU-funded project on that to use that one in the loop. And Keith also mentioned combined heat and power plants. So we used a fuel cell for just that purpose, combined heat and power plant, to power the liquid-cooled bath, and then use the heat from the fuel cells directly into the district heating network. And that is without heat pumps. So that could be an interesting solution if you have gas and if you rely on your own power production. So heat reuse combined with power production is a good one. But I also was thinking, and I think that's where Vanessa is going, is about this the temperatures of coming out of liquid cooling. You know, it has been a lot of talk the last couple of years about with liquid cooling we will get higher temperature heat out of the data centers. It has been a kind of a promise, but what we see now with the new processors, when we really need liquid cooling, because they will not be possible to cool without liquid, then we see lower TK's temperatures, lower chip temperatures, because you need to control that heat flux, and that will mean that we will get back to the temperature levels of air. So that was not that holy grail we were hoping for higher temperatures. Sorry about that message, but we need to take that into account.
Is this the was it the Grace Blackwell 200 GB200? Was it? Yeah,
for example, that one lower TK's temperature, but the coming ones will have even lower TK's temperatures than that. So the controlling temperature of maybe 50-60 degrees instead of 80 as we have now in air cooling and the low power dense chipsets. And cooling it with air, fine, but the temperature out of that system maybe 35-40 degrees, but liquid cooling 45-50 maybe in the top
limits what we can do with it, right?
But that will go down.
Mm-hmm. Interesting points. Have to see what comes of that one. So what are we actually seeing in practice? Are you seeing the 100 kilowatts a rack everywhere? I mean, are we seeing, NVIDIA stacked servers from floor to ceiling? What are we actually seeing in practice? Anyone?
If you look at the NVIDIA site for their solutions, it seems like it's 3 servers in one rack. So, and that is, of course, to make it possible for air-cooled data centers to run the system, because the stack rack full of them, then you need some other air cooling to make it happen.
Alex, what are you seeing?
We're seeing a mix. I think we are seeing, higher density applications. It's all high density, right? But we're seeing, sort of touching 100 kilowatts plus. But I think that at the moment, the higher volume of opportunities that we're seeing is more around the kind of 50 to 60 kilowatt bracket, and then stemming down to kind of kilowatt ranges, some more typical to what we would look at for high density air cooled. So, but I think it's that again, to go back to that point on hybrid architecture, it's that mixture and percentage of air-cooled versus liquid-cooled within the different racks, which is one of the key things that we're having to look at now in terms of how we develop some of the designs that are moving forward. So you could have a sort of a 60 kilowatt rack, but the liquid cooling requirement for that is only 85%, say, and so you're having to cater for the additional 15% of air cooled in a sort of conventional perimeter room cooling setup, or using supplementary in-row cooling into that particular rack. So I think there's an added degree of complexity now, and what we're finding is the engagement that we're having with customers, be it in an enterprise, co-location, hyperscale capacity. We're far more involved with characters that we didn't traditionally have that sort of engagement with, because we had this very defined barrier of air that was responsible for the cooling. It was very easy to attach to the engineering consultancies and the operational departments of the people that are running these facilities. So now
bring on the plumbers.
Bring on the plumbers, right? Yeah. And even Keith was mentioning the potential for liquid cooling UPSs, right? So the worlds are colliding somewhat, and the need to be very transparent around not just the extremities of operating conditions of the IT hardware and its requirements, but also what it looks like in a more cyclical fashion, to understand then both the control and the different type of technologies that we need to consider to cater for in different data centers is absolutely critical. And it's a fascinating development, really. This industry has perhaps been guilty of being somewhat siloed in the past, particularly between the operational world and the world of IT. And those two very much need to coexist and collaborate for this to really be a success. And given the sheer densities and the amount of power that we could stand to potentially consume, optimization of how these facilities are run is absolutely fundamental.
And this equipment's not cheap either, is it?
No.
Quite right. I think. Do you think it's going to breed a sort of a degree of transparency between the different sectors? Given that, historically, a lot of facilities have been designed based on nameplate power ratings. Are we going to have to now move to a much more realistic valuation for this to avoid the over-design capacity that's endemic in most of the facilities that we operate today throughout the world? I mean, given that capacities can rarely meet even sort of 50% load demands that were initially sort of forecast, you end up with this massive stranded capacity, massive infrastructure that's been fitted out, which all breeds sort of further inefficiencies through the system and excess costs and maintenance requirements. I think in this mass scale now, if we are going to see this increase in power demand for AI or these facilities where the power used to be, the ratio of power to IT was sort of a 1-to-1 relationship. If we're now seeing that the density of that one for the ICT is now going to demand a 10-fold increase for the power, but that's based on the nameplate ratings. So are we not going to have to challenge people to say, is this the realistic value? Is this going to be actually how it operates? And actually challenge the different facets within the data centers, not just the infrastructure suppliers, but the ICT suppliers, to actually give proper data, give realistic data to the operation of the equipment. And as Alex talks about, the optimization of these systems, how they operate collectively in the facility to perhaps be a more flexible demand basis to manage that power and obviously the cooling side associated with these infrastructures.
I think you're absolutely right. And I think we're seeing more digital twin software as well. So it's taking live data in order to be able to manage and optimize the room efficiently.
And that in turn requires even more data centers to operate it and more power to run it and optimize it. But equally, it's going to be...
You've also got You've also got the regulatory factor, right? So John was talking about, the regulation that's coming in and enforcing the need for data center operators above 500 kilowatts to publish their their annualized power consumption. So very, very quickly, the accountability for how effectively these facilities are being run relative to how they were originally designed and the intended. A lot of people don't like to use the PUE metric now, but the intended operational PUEs that were there on paper, based on, like you say, those nameplate ratings, Keith, that's going to create far more transparency, perhaps, than there has been previously, in a very good way, right? But the need to embrace the challenges of optimization from a design point of view and really understand how does this system work, through the respective load profiles of the different types of IT kits that's being deployed is really key. And how many different variants of operational models do you look at during the design phase, as opposed to just considering three different part load conditions and so on and so forth. So it's going to be really interesting. And I think obviously with the onset of AI in a design capacity, you mentioned obviously, Vanessa, around some of the digital twin setups that you can do. As an industry, we're getting far more insightful tools now that can help guide us, down that path as well.
Absolutely. And we're actually on time. So I'd just like to wrap up and say thank you. Very much to our panelists. Amazing chat and so many different areas, so many new things coming out as well. So it's quite an exciting time. So thank you very much, Kaylee. Over to you.
Thank you very much. I was going to say that was perfectly timed, and I just wanted to again say thank you, Vanessa, Alex, Tor, and Keith, for your time today. It's a huge topic at the moment, and there's a lot of unknowns going on. So thanks very much for trying to grapple that and the brevity with which you tackled it. So thank you.